Okay, so last time we have been working with the orbit determination using vector method. So, we continue with that, the last few explanation we are remaining. So, we will complete this and then move to the scalar form of the orbit determination, and which is conducive to computer implementation. So, last time we had the equation cos omega is equal to n dot e bar. So, in this equation, if the angle between n and e is lying between 180 degree, so it is fine, the whatever the value we get for the omega, that is correct, but if it is more than 180 degree, then problem arises. So, we need to resolve this. Okay. So, here omega lies between 0 and 360 degree. So, we need to resolve this. So, for dot resolving, what we did, we took the dot product of E dot and k dot vector. So, we had the E vector which was lying in the plane of the orbit like this. So, this is the E vector and k vector was along the z direction. So, this is the z direction O n and n prime was here, and in this direction we had x and here we had y, okay, and the angle it was making here, the angle of inclination I. So, if the E vector is lying above the x y plane, so E dot k, this will be less than 180 degree. Okay. So, here what we will do, that if this is E dot k is greater than 0, then we write, then we have cos omega gives the correct value of omega. So, if E vector is lying above this plane, means the z component of the E vector is positive, okay, then E dot k, the dot product of this will be greater than 0. If E vector dot product with the k vector, if it is less than 0, means E vector is having a negative component, okay, means no longer the perigee will lie above the x y plane, but it will go below the x y plane. So, in that case E dot k will be less than 0. Okay. So, from here to here, this angle is positive. Suppose it goes below this. So, the angle between on the right hand side, if it tilts to the below the x y plane. So, you can see directly that between the angle between the k and the E vector exceeds 90 degree. Okay. And here it will vary from till measuring from the angle I is equal to 0. So, if we take the extreme position that the E vector is near about I is equal to lying on the x y plane. So, the angle between the E vector and the k vector, it is around less than 90 degree or 90 degree. Okay. So, in that case E dot k, the dot product will remain positive, but as soon as it goes below this plane, so this becomes negative, and therefore, corresponding correction must be given for quadrant resolution. So, if the angle between here, the angle between E and the z vector, this is this angle here, okay, which is not. So, above the x y plane, if the E vector is above the x y plane, so this angle remains less than 90 degree, even if E is lying on this side. So, you can see that E will be again less than 90 degree, but as soon as the E goes below the x y plane, you will see that this value will exceed the 90 degree, and therefore, both these assumptions are correct. So, E dot k greater than 0 will indicate that the perigee is lying above the, this is the perigee here. So, perigee is lying above the x y plane and E dot k less than 0, it will show that the perigee is lying below the x y plane. So, accordingly the argument of perigee, okay, this can be resolved. Now, the next was true anomaly. So, for the true anomaly, again we have the cos theta is equal to E dot r, okay, where theta will lie between 0 and 360 degree, but the cos theta will only resolve between 0 and 360 degree, it will give the correct value. But if it exceeds the 180 degree value, if the angle between E and R is greater than 180 degree, then the coordinate resolution must be done as we have done for E, the dot product of n dot E or the cos omega. So, in the same way we have to follow here. So, in this case what we see that R times V, this will be greater than 0, means that implies that if we have the orbit here, okay, this is the perigee position and this is the r vector and this is the velocity vector v, the components of the r vector, this is r dot and this is r times theta dot. Okay. So, r dot v, this will be positive while we move from perigee to apogee till this point. From here to here this will be positive, okay, but as soon as we go below this, so r dot v will be less than 0 for theta lying between 180 to 360 degree. Okay, and this is valid for theta lying between, okay, so this will give correct value, this will give correct value till theta less than 180 degree, less than equal to 100 degree, 180 degree. So, as soon as we are exceeding, means we are coming into this domain. Okay. So, then we have to take care of the proper sign, and this proper sign can be resolved using these two inequalities, r dot v greater than 0 and then r dot v less than 0 for theta lying between 180 and 360 degree. So, if we get this quantity, then we are ensured that the theta is lying from here to here, and if we get this quantity, so we can ensure that it is a lying between this and this range from here to here. Okay. So, this completes our vector method of orbit determination. So, now we go into the scalar method, or say the a method which is a way which is conducive to computer implementation. So, we will work out that. So, this will be not in terms of the vectors, but this will be represented in terms of the scalars, means the components of the x components of the radius vector and the velocity vector, which are x, y, z and x dot, y dot, z dot. So, given, so scalar representation. So, given r 0 is equal to x 0 I plus y 0 j and v 0 is equal to x dot 0 I plus y dot 0 j y dot 0 j plus dot 0 k. Okay. find all orbital elements. So, here we write H is equal to R 0 plus V 0. So, if we take the cross product of this will be y 0 z 0 dot minus y 0 dot z 0 I cap 0 minus x 0 z 0 j cap plus 0 y 0 dot minus y 0 x 0 dot k. This is our equation number 3. So, H we can write as H times u n, where u n is the unit vector perpendicular to the orbital plane. So, we need to determine the u n vector. So, for this we draw the figure, the x, y and z. This is O. So, this is the perigee position. So, angle from here to here is we take a line here M whose angle is here 90 degree. So, this is M. The satellite is somewhere here in this position. So, this is the position of satellite S. This is the R vector. Okay. So, the angle from here to here, this will be 90 minus small omega, and the angle which we are measuring from the perigee, this angle from here to here, this is total angle is theta. So, this angle is theta angle. Okay. This is the z, and we have the u n vector which is perpendicular to the orbital plane. So, this is the h vector and u n is also along this direction. Now, the projection of point M on the x y plane we show like this. So, this is our M prime, and we can connect them. The projection of the orbit we can show in this way. Okay. So, the angle M O M prime is nothing but I, which is the angle of inclination. Okay. This angle from here to here is capital omega, argument of perigee. So, opposite to the O M vector we extend here and we write O M double prime. Okay. And unit vector in this direction we will show this as u O M double prime cap. Okay. Now, using this figure, so this is our figure 2. So, using this figure we will be able to work out all the details. So, from here we can write u n cap is equal to cos I k cap times cos 90 minus I u cap double prime O m. So, the angle from here to here, this is the angle I. Okay. So, this angle from here to here, this is 90 minus I. Okay. So, which is pretty clear from this figure. So, this is our equation number 4. then we write UOM cap double prime is equal to minus UOM cap UOM prime. Okay, because OM prime and OM double prime, they are opposite to each other, so this is valid. Now, unit vector along OM prime, we can write it as U cap j cos capital omega minus I sin capital omega. This is n prime O, and m prime is perpendicular to this line. This is 90 degree. Angle from here to here is capital omega. This is 90 minus capital omega. This angle is then capital omega. So, we can get the unit vector along this direction j cos capital omega, and here this is x and y, and this is x prime. So, this is minus I cos 90 minus omega, which gives us the minus I sin capital omega. So, we get this value. So, therefore, U cap OM double prime, this will be minus j cos capital omega, this is cap, plus I capital cap sin capital omega. So, this is equation number 5. So, this implies U n cap will be cos I plus k plus sin. We need to replace UM double prime. So, this becomes sin I times minus j cap cos capital omega plus I capital omega sin capital omega. Okay. So, here this is nothing but sin I. Okay. So, we are using the same thing here. Okay. So, expanding it, we can write U n cap is equal to sin I sin capital omega I cap minus sin I cos capital omega j cap plus cos I k. Okay. And h we have, therefore, we can write as h times sin I sin capital omega I cap minus sin I cos capital omega j cap plus cos I k cap. This is our equation number 6. Now, comparing equation 3 and equation 6, we can write y 0 z 0 dot minus y 0 dot z 0 is equal to h sin I sin capital omega. This is 7a, then z 0 x 0 dot minus x 0 z 0 dot is equal to minus h sin I cos capital omega 7b x 0 y 0 dot minus y 0 dot is equal to h cos I. This is 7c. Okay. So, from 7a and 7b, 7a and 7b, we can write tan capital omega dividing them minus y 0 z 0 dot minus y 0 dot z 0 divided by z0 x0 dot minus x0 z0 dot, and there is no ambiguity of sign because the separately we need the we know this term and this term. So, we are dividing this. So, depending on the sign, the in which quadrant the capital omega is lying, this can be resolved. So, this is our equation number 8. Now, 7c, from 7c we get cos I equal to x y0 dot minus y0 x0 dot by h. This is our equation number 9, and there is no ambiguity in this case, okay, because the I will lie between 0 and 180 degree. So, for I less than 90 degree, it is called the prograde orbit, and I greater than 90 degree, it is called the retrograde orbit, and for I is equal to 90 degree exactly, it is called the polar orbit. So, here there will be no ambiguity of the sign of I, because the I will vary from 0 to 180 degree. So, it lies between 0 and 180 degree. So, there is no ambiguity in this case. Okay. Now, we have unit vector along the ON direction. This can be written as I cos capital omega plus j sin capital omega, and this is very obvious from this figure. We can take the unit vector along the ON direction here. Okay. So, this is our equation number 10. Now, r 0 dot u on cap, this will be r 0 cos theta plus omega. So, here what we are trying to do, we are trying to work out the argument of Parisi. Theta is already known to us, theta we have determined in our earlier lectures. So, if we get the value of theta plus omega, which is the angle measured from the line, this is n and the n prime. So, if we measure, if we have the total angle available theta plus omega, then it will be very easy to find out, provided the theta is known. So, omega can be derived from after subtracting from theta plus omega. If we subtract theta, then we get the value of omega. Okay. So, here we are attempting to find out the value for cos theta and omega. So, this angle, we know the angle. Let us look into what this the quantity of what this value is between S and OM. So, from here to here we see that this is the angle theta, and from here to here this is the angle omega. So, this total angle from here to here is theta plus omega, and if we subtract from this the 90 degree. So, this angle will be nothing but theta plus omega minus 90 degree. Okay. So, we can utilize this to find out theta plus omega. So, exactly going through this process. So, r 0 dot u o n, this is r 0 cos theta plus omega. So, we have r 0 cos theta plus omega. Now, break this, the left hand side we are writing here, this is x 0 I, y 0 j plus z 0 k, and u o n vector we know I cos, this is I cap j cap, I cos capital omega plus j cap sin capital omega. So, this gives us x 0 cos capital omega plus y 0 sin capital omega. So, r 0 cos theta plus omega, this is this quantity, this is our equation number 11. Okay. Now, we have taken along the dot product of r 0 and u o n. Now, we can take the dot product of r dot and u cap o m. Okay. So, this will be r 0 times cos theta plus omega minus 90 degree So, this will be r 0 sin theta plus omega. So, thus this is our equation number 12. Thus, r 0 sin theta plus omega, we can write this as x 0 I cap plus y 0 j cap plus z 0 k cap, and dot product with u o m vector. So, u o m vector we already know. So, multiply this here, this is u o m we have written as cos I times sin capital omega I cap plus cos I cos capital omega j cap plus sin I k cap. This is the u o m vector we have written earlier. So, let us work out the u o m vector. So, u o m vector we can write as k cap sin I o m u o m, the unit vector along the o m direction. So, we take the component of the k vector along this. So, this is k sin I, this angle is 90 minus I from here to here. Okay, so, k sin I plus cos I times the unit vector along the o m prime direction. So, we already know the unit vector along the o m prime direction. This is the unit vector along this quantity is nothing but u o m prime. So, now we resolve this. So, if we resolve it, this will result in cos I sin capital omega I cap plus cos I cos capital omega j cap plus k plus sin I k cap. So, this is u o m, and this is what we have utilized in the previous equation. So, this is our equation number 13 and this is our equation number 14. So, equation 14 has been utilized in equation 13. So, from equation 12 we can say, from equation 13 we can see that expanding this. So, from equation 13 we can write r 0 sin theta plus omega, this will be minus x 0 cos I times sin capital omega plus y 0 cos I times cos capital omega plus z 0 sin I. This is our equation number 15. Okay. So, once we have got r 0 sin theta plus omega and r 0 cos theta plus omega. So, we can get the value of sin tan theta plus omega. So, this is 10 8. So, using equation 15 and equation 11, we can write tan theta plus omega minus x 0 cos I z0 sin I divided by x0 cos capital omega plus y0 sin capital omega. So, thus we have this will give theta plus omega, and there will be no problem in determining the quadrant, as sin theta plus omega and cos theta plus omega both are known. So, the any ambiguity can be resolved. Okay. So, in the previous lectures we have determined A, okay. We determined E, and for E we got a number of equations. Thereafter, we also determined tan theta, okay. We determined tan theta, and then we also worked out A, E, tan theta. Okay, 3 parameters we have done there. So, the rest 3 parameters we have worked out here, which are I, capital omega and theta plus omega. So, if we subtract from this theta plus omega minus theta, so this will give us the omega value. Okay. So, this completes the process of the orbit determination. Okay. So, we have a number of ways of finding the value for E. So, you can go in the previous lectures and look for all these things. I need not repeat all this again. So, this is 10:9. Now, the reverse problem of orbit determination we take. So, the reverse problem of orbit determination, that is given A, E, I, small omega, capital omega and theta, find x, y, z, x dot, y dot, z dot. Okay. So, for this we need the help of figure 2. Okay. So, very easy to work out. Here what exactly we do? We have this vector r, this is the r vector available to us. So, break this r vector along the O n prime direction, okay, along two perpendicular directions. So, O n prime and O m. Okay. Thereafter, break the O m along the z direction and the O m prime direction, okay, which is lying in the x y plane. Then break the O m prime along the O x direction and O y direction. Similarly, break the O n prime along the O x and the O y direction. So, the corresponding components, if you add, you get the x component of the radius vector. Similarly, you get the y component of radius vector, and z component is available here. And if we take the derivative of this, then we get the corresponding velocity components. So, we write here resolving r vector along O n prime and O m direction in figure 2. Okay. So, r vector we are resolving along O n prime and O m direction. So, this will give us r sin theta plus omega minus 90 degree, this is equal to minus r cos theta plus omega. Okay. Similarly, this will give r cos theta plus omega minus 90 degree. So, this gives us r sin theta plus omega. Now, O m prime, the component O m can be broken along the z direction and the OM prime direction. So, next we break the component OM along the OZ direction and along the OM prime direction. So, along the OZ direction, this will give r sin theta plus omega sin I, and this will give r sin theta plus omega cos I. Okay. So, next we need to break OM prime along the OX and the OY direction, So, breaking this r sin theta plus omega cos I and sin capital omega. Similarly, this will give us r sin theta plus omega cos I times cos capital omega. Okay. And this you can very easily observe from this place, because these angles are known. So, we are breaking up OM prime. So, angle from here to here, this is capital omega, and this angle is also known. The angle from here to here, this is 90 degree, which is lying in the xy plane. So, this angle from here to here, this is also known. Okay. So, this angle is capital omega, this angle is capital omega here. This is 10, 11. Okay, once we have broken the OM, next we need to break OM prime. OM prime we have already done. So, next we go for breaking up ON prime. Okay. So, break ON prime along OX and OY directions. So, we can take help of the figure here. This is x, y, this is n prime, okay. And here this is O, this is our m prime m. This angle is capital omega, this is 90 minus capital omega, here this is capital omega, minus capital omega, 90 minus capital omega. So, what we need to break ON prime along the OX and the OY direction. So, ON prime, breaking this along the OX direction, this will give us ON prime is minus r cos theta plus omega, okay. And the angle from here to here, this is nothing but 180 minus capital omega. So, this becomes cos 180 minus capital omega. So, this becomes equal to r cos theta plus omega plus cos capital omega. Similarly, we break OY. So, this will give us r cos theta plus omega, and along the OY direction the angle is 90 plus capital omega. So, this becomes cos 90 plus capital omega. So, this becomes equal to, here this minus plus r cos theta plus omega, and this becomes sin capital omega. Okay. So, now add all the components along the OX, OY and OZ direction. So, this is 10 13, adding all the components along the O x O y directions. Okay. So, if we add, we get the corresponding x, y and z values. So, x will be given by minus r sin omega plus theta cos I times sin capital omega. You can check one by one. So, this is the component here O x, we have taken r sin theta plus omega cos I times sin capital omega, which is appearing here. Next, another component of O x, okay, another component of the O x is r cos omega plus theta times cos capital omega. Okay. Similarly, the y can be written as r sin omega plus theta cos I times cos capital omega, r cos omega plus theta times sin capital omega, and z can be written as r sin I times sin theta plus omega. You can verify this. So, O z component, you can see here O z component we wrote like this, r sin theta plus omega sin I. So, this is the same thing. Okay. O x component, this part is okay. We broke O m prime. So, here this is O x is cos O n prime O m prime. Okay. This is O m prime, we have broken along the O x direction and the O y direction. So, for O m prime we had here O m prime is given here itself. Okay. So, this O m prime we are breaking along the O x direction. So, along the O x direction, this is r sin theta plus omega cos I, which is copied from this place, and then the along the O x direction. So, O m prime once we are breaking. Okay. So, this angle from O m prime from here to here, the angle between this and this is 90 plus capital omega. So, cos 90 plus capital omega. So, this here this should bear a minus sign. So, here this is with a minus sign. On the page number 1011 we have a correction here, this is so, this we have got from okay, the angle between O m prime and O x is 90 plus capital omega. Okay. So, once we take cos 90 plus capital omega, okay, so this is equal to sin capital omega with a minus sign. Okay. So, this is what has appeared here in this place. So, the minus sign here should be introduced. So, this is O x is equal to minus r sin theta plus omega cos I sin omega, okay. And the last component we add to this was O x, which was written here r cos theta plus omega times cos capital omega. So, this component we have put here in this place. Okay. Similarly, we can complete for the y and z. Okay. Okay. Now, once we have got these values, so if we differentiate x, y and z with respect to t, okay, then we will get the, once we differentiate x, y, z with respect to t, then we get x dot, y dot, z dot. We have to take care that only theta is a function of time, only theta is a only theta is a function of time. Therefore, only the derivative of this will be taken. So, now taking the derivative of x dot. So, x dot will be given by, so we go back to this slide and number these equations. 15, we can write this as let us say write this as 16, this as 17 and this as the equation number 18. Okay. So, from equation 16 x dot becomes equal to, okay, here only theta is a function of time and theta and r, only theta, r and theta are function of time. So, if we differentiate, so from equation 16 we can write r dot times minus sin omega plus theta cos I sin capital omega plus cos omega plus theta cos capital omega, okay, plus r times minus, okay, here theta is coming inside. So, we have to differentiate this. So, if we differentiate this, so sin will become cos omega plus theta and theta dot will appear, okay, cos I, okay, sin capital omega, and here again the, if we differentiate cos omega plus theta. So, here we have to write sin omega plus theta with minus sign and cos capital omega, and theta dot will appear. So, theta dot appears in both these terms. So, we write theta dot outside here. Okay. So, this gives us the, this is equation number 19. This gives us velocity in the x direction, velocity component in x direction. Similarly, y dot we can write from the equation number 17. So, y dot will be equal to r dot, okay, sin omega plus theta cos I cos capital omega plus r cos omega plus theta sin omega, okay, plus r times sin derivative will be cos omega plus theta and theta dot. So, theta dot we will take it outside later on, the cos I cos capital omega, and here this term, here r is not there, okay, r we have taken outside here. So, this becomes minus with minus sign here, sin omega plus theta times theta dot sin capital omega, and theta dot we take it outside and write here in this place. And similarly, z dot we can write as by taking the derivative of the equation number 18. So, z dot will be r dot sin I times sin theta plus omega plus r times sin I, and sin theta derivative will be cos theta plus omega times theta dot. So, theta dot we write here in this place. Okay. So, this is our equation number 20 and this is equation number 21. Now, we know we have started with the A E. We were given A E I small omega, capital omega and theta value. Okay. So, from there we need to we are finding this x dot, y dot and z dot. So, we can use few substitution, and so what we need to replace here r dot and the theta dot. Okay. So, theta dot we know that theta dot is equal to h by r square, okay, and r square is nothing but x square plus y square plus z square, which also we have written as L by 1 plus e cos theta, okay, and L is nothing but a times 1 minus e square by 1 plus e cos theta. Okay. So, therefore, E is known, A is known, okay, theta is known, E is known here. So, therefore, R can be calculated here, R is equal to this quantity. So, R is known. Similarly, H can be calculated. Okay. H is nothing but h square is equal to mu times L. Mu is known, L is known. So, this is mu times a times 1 minus e square. Okay. So, therefore, from here h is also known. So, theta can be determined. So, theta can be inserted in all these, theta dot can be inserted in all these equations. Okay. And r dot also similarly can be determined, because r is equal to L by 1 plus e cos theta. So, we can take the derivative of this 1 plus e cos theta. Earlier we have done this exercise, e cos theta square minus, so this becomes e cos theta becomes sin theta and then times theta dot, and this will become plus. Okay. So, again all the quantities here are known, L is known, E is theta, and here all this quantity is known. Theta dot already we have determined from this equation. So, using these informations we will be able to write the equation for r dot also. So, this completes the process, reverse process of finding out x, y, z and x dot, y dot, z dot. Okay. So, we can write in a proper way. This is 1 by L plus e cos theta times, or we can write L by 1 plus e cos theta square divided by e sin theta times L times theta dot. So, this becomes nothing but r square divided by L times e sin theta times theta dot we can replace by h by r square. So, this cancels out, this leaves us with h times e sin theta divided by L. Okay. So, this is the final we are getting, r dot becomes equal to h times e sin theta by L. Okay. So, we have got here the value for r dot, we have got from here the value for theta dot. So, our process of the orbit determination is complete. Okay. So, next lecture we will look into the Kepler's equation of motion and the Kepler's problem. So, Kepler So, Kepler equation, Kepler's problem, it's and Kepler equation of motion, they are related together, but they are definitely different. So, we will look into that problem. Thank you very much.